Hey, welcome back to CE 529. This is week 3. So, or week 2, really, if you think of the first week as week 0, because we only had one class then. So, what we are talking about, so I just want to quickly go over some stuff from the last class. That the idea of route choice, right? So this is sort of what we are dealing with. And in today's session, we are going to pick up on the discussion of the dynamic routing. So how do we sort of do a time-dependent routing of travel demand through our network? But before that, I think it's very important for us to be very clear about what is the role of user equilibrium in traffic, and what kind of thresholds you are establishing when you're splitting traffic between the network. And I see there were only 5 responses, which is fine, but it looks like, so there was this question about how do we establish thresholds when we are dealing with trying to assign traffic on the route. So that threshold question is very critical. Obviously, it's part of your homework, so I hope you got a little bit more clarity on that. But I want to talk a little bit more about that. So give me here, let me open up my So I'm going to go ahead and open this traffic assignment problem, right? So let's think about this problem real quick. We talked about it, and it's a very simple problem. And the idea of threshold is always, always, the route that has the worst free flow travel time is at the risk of not being used. Right? Now, one thing I want you to think about is that a lot of times you might be assigning traffic between certain origins and destination in your network, but your network itself might be larger. Your network itself might have sort of other connections that might be feeding traffic to it. So I want you to think about that scenario as well, because I know there were some concerns about the threshold. So I want to make sure that we can make clear that this threshold question is very important, especially so is when you're modeling larger networks. Because you might be assigning traffic between certain origins and destinations, but those OD pairs might not be the only ones that you need to serve. Those routes might be serving other places as well, other origins, other destinations as well. So what is the implication for you in a problem like this, in a problem that you're seeing on your screen? So what I want to do is, I want to first of all stop the share, and second of all, okay. So I'm going to redraw that problem, my traffic assignment problem. So I might have origin, a destination, and I'm just going to do 2 routes for now, because I think the concept of threshold is pretty clear even with 2 route problems. But 3 is equal to 4 plus 3x1. It's basically the same problem that we saw before. And T2 is equal to 2.2 plus 6x2. Right? So this was the issue that we were dealing with. Now, you know that this is the route at the risk of not being used. So this is the route that will get used first. But what if I told you that these OD pairs, and then, so the question of threshold is pretty easy to determine. You say, okay, I want to make sure, I want to start using this route when this travel time becomes 4.2. So I'm gonna be able to establish that threshold that way. If I had more routes than that, I will make sure that I put the worst performing travel time route. All of my routes, all of my remaining routes should have at least that much travel time. That's only when that last route gets used. Otherwise, it doesn't. Now, sort of complicating things a little bit here. Remember, we were making decisions based on these free flow travel times. What happens if this, as I said, this OD pair is part of a larger network, and that network is feeding, let's say, certain amount of traffic to these both of these routes. So instead of these routes being empty at the beginning when you start assigning traffic, you have what we call some existing traffic. You have some existing traffic. So you have some given demand of 3,800 vehicles per hour. You have a given demand of 3,800 vehicles per hour. But you also have existing traffic on both these routes, and I'm going to give you some numbers here. On this route, there is existing traffic of 1,000 vehicles per hour on this route, and 800 vehicles per hour on this route. Again, this existing traffic is independent on what's happening between this ODP. Okay, these routes are being used by other folks. Okay, now how would the problem change, do you think? So the question we want to answer is, how would the problem change if this is the situation, and then you have 1,000 vehicles per hour existing traffic, and then 800 vehicles per hour existing traffic on Route 1? Yes. Equation. Yeah. So instead of making, so this is right. If they are fixed and known, you know that this existing traffic exists independent on what happens to this demand, at least for now, then you could sort of apply this concept into it. And instead of making decision based on these free flow travel time, I cannot establish my thresholds now based on these free flow travel times anymore. I will need to figure out what is my sort of effective free flow travel time. My effective free flow travel time in this scenario would be, so I'm going to just call it T2F prime. So effective free flow travel time would be 2.2 plus 6 equal to 8.2 minutes, right? Because X2, 6 times 1, I should say, because 1,000 vehicles are in there. So I should say 2.2 plus 6 times 1 gives me 8.2 minutes. Similarly, I can determine T1F prime, the effective free flow travel time on Route 1, and that would be what? That would be 4 plus 3 times 0.8, right? 800 vehicles per hour, 0.8. And that would be 4 plus 6.4. Make sense for everybody? Now, what would be happening next? For these are 3,800 vehicles per hour. Which route is at the risk of not being used? In this scenario, this one, right? This is the route that now has worse free flow travel time. Not exactly a free flow travel time, but the effective free flow travel time now is higher over here. Okay. So now your threshold calculations change a little bit. So now let's take a minute to determine what do you think will be the threshold at which both routes start to get used for this 3,800 vehicles per hour. Okay, your worst free flow travel time now is Route 2. Okay, so Route 1 will start getting used first in this scenario. But I'm asking you, under this scenario of existing traffic, which route or at what demand level between this OD pair do both routes start to get used? Yes.
Will the coefficients be the same for
coefficients will be the same. That's basically what we are assuming. And that sort of transitions us into what we are going to talk about today a little bit later, is the dynamic traffic assignment. That's when you start to get into, like, what if these coefficients change? What if there is different variability over time in how the link behaves? For now, these coefficients remain what they are. As you add more traffic to it, the travel time changes based on these coefficients themselves. Go ahead. Okay, let's see. Zoom. Pause the recording. So the question is, this existing traffic, is that included? It's not included in the 3800. It's something, because these routes are part of a larger network, this traffic is serving other OD pairs, other origin destination pairs. So no, so this is not part of the 3800. The process is exactly the same what you did before. So instead of having the free flow travel time, the actual one, like which is 4 and 2.2, now instead you have 8.2 and 6.4. And then obviously the route, which route is at the risk of not being used, has also flipped. Okay. Anybody has that number? No? 600? Okay. So the answer I'm getting is 600. How many of you got 600? Okay, 1, 2, 3, 4. Okay. For those who didn't get it, what's the question? Do you have any questions that you can ask me? What is tripping you up here? Okay, so let me sort of try to explain this. So what's going on here is now think of these as your free flow travel times now, 6.4 and 8.2. Assume that everybody goes to route 1 initially, and they keep going to route 1 until the route 1 travel time becomes equal to 8.2. Until route 1 travel time becomes 8.2. So what has to happen? 2.2 plus 6x2 has to become 8.2. Okay. And then if you solve for this, 6x2 equal to 8.2 minus 2.2, which is 6. Then x2 equal to 1. No, did I do something wrong? Did I do something?
I put it like
Did I do? Oh, I think I made a mistake because it should be 4 plus 3. Sorry, it should be, this is incorrect, right? I should be using this one, 4 plus 3 x1 equal to 8.2. And then this will become 8.2 minus 4 is 4.2. 3x1 is equal to 4.2. And then you can solve for x1 equal to 1.4. So I'm getting 1400 vehicles per hour. I did not get 600. Yes. Yeah, see, that's the question, right? So this is way of thinking about this is that now think about, so this x1 represents the total demand, total traffic that is using route 1. And this x2 represents total traffic that is using route 2. Okay, so that's why when I'm trying to figure out what happens on my routes, because what I'm looking for is at what point the travel time on this route becomes 8.2. So my total equation is 4 plus 3x1 when travel time on this route becomes 8.2. So 4 plus 3x1 has to be equal to 8.2 for these routes to be used. I get 3x1 equal to 4.2. I got x1 equal to 1.4. I got 1400 vehicles per hour. So the total demand on this route has to be 40, or the total demand on this route has to be 1400 vehicles per hour before this route starts to get used at all. Okay, and how would that demand be 1400? 800 are already there. So you can, out of this 3800, you can fit in 600 over here, at which point our new demand also starts to get both routes. Okay, not before that, not before that. Does that make sense? Questions? Yes.
Why didn't you just establish the new threshold where in that equation you do 6.4 times the next one? And then you get 600 vehicles.
Okay, so what's how should I have done it?
I just did 6.4 plus 3x1.
6.4 plus 3x1. See, okay, so the question is, why didn't we do it exactly the way we used to do it? So, and then say 6.4 plus 3x1 equal to 8.2. Okay, so this is what I'm being asked is, why didn't we just do it this way? It gives the same answer probably, right? Because you get x1 equal to 600. Now that has something to do with how you define x1. Your equations should still make sense, right? So I don't want to change the definition of x1 and x2 because I want to define x1 and x2 as the traffic that is using those routes. If I change this definition now, I'll probably get the answer for x1 right in terms of the 30 part of the 3800 that will trigger both routes being used. I will get that correct. But now I'm getting a little bit confused about anytime I see x1, what do I put? What number do I use? And then when I'm trying to establish the equilibrium, I might get confused as to what answer am I getting? Am I getting the answer for x1 and x2 for this 3800? Or am I getting the total? Right? But if you do it this way, if you do it what I was suggesting, by not changing what x1 actually means, keeping the definition of x1 the exact same that was specified in the problem at the beginning, that would ensure that whatever answer you get, you know it's going to be in terms of the total flows. You know it's going to be in terms of the total flows. That makes sense? Does that answer your question? Yeah? Yes. Okay.
So we got the 1400, and so we are subtracting the 800 of existing traffic?
Yeah, so what we are saying is that for this demand that goes between this origin destination pair, until that demand exceeds 600, only this route will get used by that demand. So we are subtracting, yes. So to get the answer of what demand threshold exists between for this OD pair threshold, that threshold is 600 vehicles per hour. So anything below 600, you will impute all of that demand to this route, and nothing goes to this route because existing travel time on this route will still be higher. And you can't tell me that why don't these 1000 vehicles per hour switch the travel time, because their travel time is lower by using this route, because this is not what they're trying to go. They're going somewhere else. Make sense? Right? Because when you establish the equilibrium, let's say the demand was 500 vehicles per hour, right? 500 vehicles per hour demand. If you had 500 vehicles per hour new demand between OD pair. Let's say if you had 500 vehicles per hour of vehicle demand, what I'm telling you is that my threshold is 600. So everybody should just go take this route, right? So my total demand on this route would be 800 plus 500, 1300. And my travel time on route 1 would be, in this scenario, my travel time on route 1 will be, I'm going to try to take this out. My travel time in this scenario would be on route 1, it will be 4 plus 3 times 0.8 plus 0.5. And that will give me 4 plus 33.9 plus 4, 7.9 minutes. Okay, my travel time on route 2 in this scenario would be 2.2 plus 6x2. Right? Now, user equilibrium, we always said that travel time would be equal. So what's going on? Why isn't the travel time equal? Why don't people from route 2 switch? Why don't people from route 2 switch to route 1? Yeah. It didn't meet the 600 demand, so that's why they're not switching. But the whole point was minimizing a travel time. So why aren't these 1,000 vehicles per hour switching? I think I answered that just maybe a couple of minutes ago. Because these thousands are not going here. They are not part of this OD pair. They're going somewhere else. They are part of this whole universe where there could be another origin somewhere here, another destiny somewhere. So they are just sort of, there to clog up the traffic, I guess, right? At least for this OD, as far as this OD pair is concerned. So there are some sort of interesting things that happen. And I'm glad there was somebody who indicated a 3 on that threshold, because that gave me a chance to sort of initiate this discussion. So, and again, now if the threshold exceeds that value, once you go above 700, yes, now these guys at 3,800 demand, these folks will have to use both routes. Then you're safe to declare the travel time for these 3,800 has to be equal. Okay, so let's solve this problem. Let's take another minute or so to now solve this problem for the demand of 3,800. So now let's see. We already established the threshold of 600. Now let's try to solve the 3,800 demand problem. And this is going to be a little bit non-trivial, by the way. You're going to have a little bit of a non-trivial problem in your hand. First of all, because yes, you can say that 4 plus 3x1 equal to 2.2 plus 6x2. You can say that because yes, travel time will be equal once you exceed that 600 threshold. And then both routes are being used by these folks, right? Travel time would be equal on both routes. It has to be once you exceed that threshold, right? So this is fine. But is this fine? No, this is not good. This is no good. X1 plus X2 is not going to be 3,800. What is it going to be though? 3,200. No, not 3,200 either. X1 plus X2 is the total flow that is right now. Yeah. I heard the right number now. See, X1 is maybe you can think of that like X1 and X2 are the total demand flows on these networks. So what would be total demand flows on these networks? It will be X1 plus X2 will be equal to this 3,800 plus whatever was going on those routes before. So X1 plus X2 actually have to be 3.8 plus 1.8 that existed before. Okay, so solve this problem. I want to see what answers you get. So the travel time. So now I can probably solve for this. X1 plus X2 should be 5.6. But remember, this is only applicable once you meet that threshold. Before that, you just have to make sure that you allocate all traffic to the best travel time route. Yes. Anybody has the answer for me for X1 and X2? Anybody has the numbers?
So why would you add 3.8 and 1.8 again?
Yeah. So remember in our problems that we were doing before, we never had any background traffic. And the way these equations are written for the travel time, they represent all the traffic that is on route 1. This X2 represents all the traffic that is on route 2. Okay. So X1 plus X2. So X1 has to account for 800 plus whatever part of demand comes through this route. X2 has to account for 1000 and whatever part of demand of this 3800 that takes route 2. So when you add up X1 plus X2, it cannot add up to just 3.8 because that is missing these two pieces. These demand has to be accounted for because X1 and X2, the way they are defined is the traffic that is using route 1 or the traffic that is using route 2 for X2. So that's why they have to be. So that's why when you add up X1 and X2, it has to include this demand because you're doing conservation of flow. It has to account for this demand that you're trying to accommodate, plus the 1000, plus the 800. Maybe we'll need a homework problem on this too. Okay, does anybody have the numbers for X1 and X2? Because even when you get that answer, there is something else that we need to think about. Yeah, anybody has the numbers, please? Yeah, 2.06, 3.54. Let's call it 5.4. Let's call it 5.4 just to kind of. So this is the number we got: 3.54 and 2.06. But the question I'm going to ask you is, how would this demand split itself between the two routes? That's not the answer for that yet. How do you get the answer for how the demand of 3800 would split themselves? Yes.
Can you just subtract the?
Yeah, that's exactly what you're going to. X1 is giving you the answer for how many people are actually using the whole of this route, right? But 1000 vehicles are there independent of this 3800. So the demand that's used, that's going to be splitting this 3800. So your answer would be to split the 3800 the way they're going to do it. OD demand on route number 1 will be 3.54 minus 1.0, 2.54. And then on route 2, it will be 2.06 minus 0.8. That will be 1.26. And those things should add up to 3.8. Yes. What did I? Oh, yeah. So I did the opposite then. Okay. Yeah, you should be subtracting this. That's correct. 0.8 for route 1. 1.06. That's good. You guys are paying attention. What's that? Before 2 times. Like that. And then you do add them up, you will get that 3.8. So the idea of equilibrium, when we are thinking about sort of larger networks, and again, obviously we cannot track all of this. Like if you have a larger route, you're doing equilibrium assignment, stuff like that, you cannot track all of this using, what we are doing right now. But those are the ideas that sort of build that bigger algorithm of, sort of doing all of that. So probably we didn't like a mathematical programming class for that, but this is the idea there. This is how you sort of think about it. Questions? Yes.
Would it be easier if you just add x1 plus x2 equals to 3.8
Mm-hmm.
and then use the new threefold count of the calculator?
You could do that too. Yeah, you could do that. So what you're so then I will probably not call them x1 and x2. I'll probably call them maybe x1 prime and x2 prime. So I'll start there. So that's one thing you could do, is that you can. So what he's suggesting is, why could we call them x1 prime and x2? So you didn't suggest that, but that's what I'm suggesting, that if you decide to do that, I would probably call them that, you're looking for x1 prime and x2 prime, like two different variables, where x1 prime is the OD demand that uses route 1, x2 prime is OD demand that uses route 2. X1 prime and x2 prime, those new variables would add up to 3.8. And I can't directly substitute those x1 prime and x2 prime into it. And I'll just add, so instead of actually updating the free float time, I will, if I do decide to go that x1 prime and x2 prime route, this is what I'm going to do. I'm going to say, so I'm going to say T1 will be 4. Instead of updating the free float travel time equation, I will just say 3 times x1 prime plus 0.8. And T2 will be, what do you call it? T2 will be, 2.2 plus 6 times x2 prime plus 1.2. Is that right? Yeah. Okay. And now I can go ahead and solve for x1 prime and x2 prime. And I can even do now x1 prime plus x2 prime equal to 3.8. Okay. So that's another sort of way of doing the same problem. And instead of sort of back substituting, you come up with those variables. So, but the key question is, you have to be very, very clear as to how you're defining your variables. What do your variables mean? Do they mean the total traffic, or do they mean the OD demand, part of the OD demand? So if you define your variables like that, you could do this. Okay. All right, so this is great. So what I'll do is, like, I'll make a note for myself. I'll make a note for myself that I need to post a homework problem on this. All right. Okay, so what we'll do next is, pause the recording.
I heard it's showing up on Canvas.
Oh, I don't, okay. Let me resume my recording, and I'll talk about the dynamic traffic assignment. So now what we're dealing with is trying to extend the idea of these static assignments. And what I'll do is, like, maybe next 10 minutes or so, I'll make a case for, why might we need dynamic traffic assignment? Now, in most cases, you can get away with, in a lot of cases, let me not say most cases, but in a lot of cases, you can get away with just doing the static assignment within vSim. Whenever you're dealing with traffic, you can just do static assignment and you're okay mostly. However, there are situations where the dynamic traffic assignment becomes sort of important to do. Not only important, but, like, sort of almost critical to do. Okay. And then we want to talk about when does that happen. So if the route set and flows are predefined and they remain unchanged throughout the situation, the flow rates could still change, but you could do the link performance function at least remain the same. In a static model defined for a long time of day, such as the peak period, the congestion property of each links are decided by the link performance function. And link performance functions were these little equations that you saw, T1 equal to 4 plus 3x1. But if you want to be a little bit more realistic, you will see, and I'm going to show you some of those, that not necessarily, they don't necessarily have to be these simple equations. They can actually be, in fact, they are a little bit complicated equations. Usually, the travel time changes by an exponent of these x's, not just linearly, but maybe x raised to power 4 or 5, something like that. Okay, so in a static model, defined on a long period of time, the congestion property of each link are defined by LPF, the link performance function, represents the average travel time. Okay. So here are some issues with that. Like if you sort of go with that model, we always do what we did here was the conservation of flow. We always conserve the flow. And that was one of our equations when we did the static traffic assignment problems. Right? But that may not always be the case. Sometimes inflow can be more than the outflow. You know, that would happen when you have severe congestion, for example. You know, you might be modeling a situation where your time horizon for modeling doesn't go long enough, and you're modeling a situation where the queues remain in place. So in those scenarios, you cannot say inflow equal to outflow, because there will be traffic stuck in congestion and they haven't made to the point where they can leave the network. And there could be various reasons for that. So for example, merging 2 lanes into one effectively reduces the capacity of each of the 2 merging lanes. And if your interest in modeling stems from you want to see what happens in that congestion, and maybe you have these spots in the network all over the place, then maybe you need to have some accounting for that the conservation of flow might not apply. And then weaving lane change maneuvers that cross over each other also reduce link capacity. So sometimes when we are specifically dealing with weaving segments, you might have queuing in that weaving area, and those queues might persist for a long time, even beyond your modeling horizon. And again, that's where you might be in a situation where inflow may not equal to outflow. Okay. On arterial streets, traffic signal reduce the outflow capacity of links. And if a link is at time, it is red. So what I'm trying to give you is there are situations, if you go sort of in a shorter time horizon, your equilibrium assumptions do not hold up very well. Like, for example, if you're trying to model like a traffic within a signal cycle, you would always have, especially if you have oversaturated flow on a signal, oversaturated flow being, the light turns red, it turns green, but it turns red again before it can discharge the previous queue, right? So in those types of scenarios, if you're modeling one particular cycle of the signal, you cannot apply your conservation of flow, principle. And then if you're looking at both freeways and arterials, there is always oversaturation areas. And then those oversaturation conditions, they might warrant what we call the dynamic traffic assignment rather than the static traffic assignment. And then oversaturated flow. So your static assignment works really well when you're dealing mostly with sort of this top half of the figure, right? But sort of the queue discharge flow and the oversaturated conditions, this is sort of where it becomes very tricky. Now, if you look at this portion of the curve, Looking at this portion of the curve, things work really, really well. But as soon as you get over here, then things become sort of problematic. And then, you know, if you're modeling an area where these are the conditions that prevail, if they prevail for a little bit, you could get away with doing just the static modeling. But if this is sort of your norm of your peak hour, then you need to get into that dynamic traffic assignment situation. So that's the issue. And it's not like you cannot model anything with the static models, but if you want to get, depending upon how much accuracy you need in your model, you might need to model it in a time-dependent way. Now, one more thing about this chart is that if you look at this chart, you can see that the speed of traffic is basically remains constant, and you can add a lot of flow onto freeway lanes. And this is I-405. You can add a lot of traffic to the freeway lane before things start to break down, right? But once they do break down, man, it's just disaster after that, right? So you can add a lot of traffic, but then suddenly, so the straw to breaking the camel's back, things can, so you could maintain this flow for a little while, but even like, you know, sometimes one slow driver, maybe one glance at the phone or whatever, then things could break down very, very quickly, right? So this is sort of what this is indicating. And this is what I was saying, that your real link performance functions are not linear in nature. Okay? They're sort of exponential functions of not just the volume itself, but sort of like a volume to capacity ratio, where your capacity sort of lies over here somewhere, and your volume is, you know, this on the x-axis, your capacity is somewhere here. So if you're far from the capacity, things can move along, because that ratio of volume to capacity is low. But once you start to hit it, like, you know, 0.8, 0.9 for your volume to capacity ratio, the travel time just sort of explodes because speed comes down very, very quickly. So this is area of the oversaturated flow, and then this is the area of the Q discharge flow. So static assignment cannot capture queuing, as I was saying, especially in the large V by C ratio areas. Generally not appropriate to analyze either like severe traffic congestion effects or many of the measures that need to be taken to address congestion. So anytime you're dealing with, like for example, you have a bigger network and you are dealing with ramp metering or variable speed limits, and you just don't have one route, you have multiple routes which people can choose, and you're probably better off doing dynamic traffic assignment. So this is sort of the real world volume delay function, or this is the old name nomenclature for the link performance function. So volume delay function are the same as the link performance function, same thing. But you can see that there are two routes. They have sort of capacities. The total 1 hour demand is 1 and 2, 2,500. Even though these models that you see might be very complicated in nature, I think you can make the case, you can solve that equilibrium problem, I think, even though the models might be very complicated. Because if it's not a linear variable, if it's like something raised to power 4 or whatever, and by the way, this is what that function looks like. Starts out slow, but then sort of explodes afterwards as you move to the right. And then similarly on the blue line, starts out slow and sort of explodes afterwards. Right? So this will be something like an exponential function. So x1 over capacity raised to power whatever. And but still, you can solve this problem. The math will be a little bit complicated. Maybe you can use some online tool or whatever and solve it. Right? Because the total demand is only 2,500 and the link capacity actually is 1,800 plus 1,200. Okay, so 3,000, right? So link capacity is higher than your demand. And then the good news is that, you know, you could sort of go back and you can actually solve it graphically. That at 1,000 here and 1,500 here, the travel time on both links is 15 minutes. Okay, just a simple And I'm making up these numbers because I don't have the equation, but what I did was I drew a line at the same travel time. Okay, at the same travel time, wherever that line meets, that becomes my equilibrium travel time solution. And whatever these horizontal values means become my sort of my travel volumes at which that equal travel time would occur. So that's a problem we have solved, even though in a simple form. But now look, what happens if you are sort of dealing with the total demand being 4,000, the travel time would sort of become really, really large. You know, you're dealing with, there's no sort of correlation between how the travel time increases. You put in the demand is like only 1,500 up, but now the travel time is 5 times higher than it used to. Okay. So I'm going to stop here. We're going to make the case for sort of do a little bit more with the dynamic traffic assignment on Thursday. I'll see you in the lab today. We'll start our first VSIM assignment today. With that, I'm going to stop and I'll see you at noon.